The John Deere D was born in an era when brute force still ruled the fields, when raw mechanical strength mattered more than comfort, more than efficiency, and sometimes even more than reliability. It was a machine that promised to pull what no horse team could, to work longer days, to reshape what was possible on American farms. But hidden beneath that promise was a weakness that countless farmers would only discover when it was already too late. A cooling system that simply could not survive the relentless reality of heavy agricultural labor. Before we go any further, let me pause for just a moment. If you are enjoying this kind of deep, honest documentary about agricultural machines, I truly ask you to support us. We are a small channel, built by people who genuinely love tractors and agricultural engineering. Please subscribe to the channel, leave your like, and share this video with a friend who is also a fan of farm machines. This makes a real difference for us and helps this project keep growing. Now, back to the machine. The John Deere D was equipped with a massive 2-cylinder engine, designed to deliver slow, crushing torque. On paper, it was exactly what farmers needed for plowing heavy soil, pulling large implements, and working long days without stopping. But in practice, that same engine produced intense and constant heat. And here is where the first chronic factory flaw revealed itself. The cooling system was not designed to dissipate that heat efficiently under continuous high-load conditions. Its radiator, airflow design, and coolant circulation were all engineered for moderate duty cycles. In real field work, especially during long plowing sessions in hot summers, the system reached its limit far too quickly. Farmers would notice the temperature creeping higher and higher, often with no immediate warning other than a faint loss of power and an unusual smell of overheated metal and coolant. Once overheating began, the consequences were severe. Cylinder heads warped. Pistons expanded beyond their tolerances. Oil thinned to the point where it could no longer properly protect moving parts. What started as excess heat quietly turned into permanent internal damage. Many engines that should have lasted decades instead required rebuilds after only a few harsh seasons. What made this flaw especially dangerous was how unpredictable it felt from the operator's seat. A farmer could work for hours without problems, then suddenly face a dangerous thermal spike without any advanced indicator. Temperature monitoring was primitive, and by the time the operator realized something was wrong, the damage was often already done. In regions with heavy clay soil, the problem became even more dramatic. The tractor was forced to operate under maximum load for long, uninterrupted periods. The engine worked at full effort, the cooling system struggled to keep up, and heat accumulated faster than it could be released. On hotter days, the margin of safety disappeared entirely. Many farmers tried their own field solutions. Some added auxiliary water tanks. Others modified fan blades or ran with partially open radiator caps to relieve pressure. A few even installed non-original radiators with larger surface areas. These solutions helped reduce the risk, but none of them truly corrected the original weakness. The core problem remained embedded in the factory design. Cold climates brought a different side of the same issue. The tractor struggled to regulate temperature properly in winter. Farmers often used makeshift covers over the radiator to prevent overcooling during startup, only to forget to remove them later. Once the engine reached working temperature, the restricted airflow would suddenly push it into dangerous overheating territory again. The cooling system had no flexibility. It was either insufficient at high load or unstable in changing conditions. Over time, this flaw quietly reshaped the reputation of the machine. While the John Deere D earned admiration for its pulling power, it also developed a shadow reputation among experienced operators. Many would describe it as a tractor that demanded constant vigilance over its temperature. You could trust its strength, but never fully trust its ability to survive a long, unforgiving day in the field without careful monitoring. Workshops across rural America became familiar with a specific pattern of damage on these engines. Burnt valves, cracked heads, scored cylinders, blown gaskets. All different symptoms, but with the same root cause: excess heat that the cooling system could not properly manage under sustained stress. This was not a flaw that showed itself immediately. It appeared slowly, silently, often disguised as normal wear. By the time the owner understood what was happening, the financial damage was already unavoidable. For many small farmers, a single major engine repair could mean selling livestock, delaying planting, or taking loans just to keep the tractor operational. Despite its legendary status today, this cooling issue represents a hard truth from the era of early heavy tractors. Engineering ambition advanced faster than thermal management. The John Deere D pushed mechanical limits that its own cooling system was never fully prepared to support. This first hidden problem was not loud. It did not announce itself with dramatic breakdowns on day one. Instead, it eroded the machine from the inside, season after season, heat cycle after heat cycle, until strength turned into fragility. The second hidden problem of the John Deere D was not something farmers noticed in the first days or even the first months of ownership. It revealed itself slowly, through fatigue, through resistance in the controls, through subtle mechanical reluctance that grew worse with every heavy pull. At the heart of this issue was a brutal mismatch between what the engine could deliver and what the clutch and transmission were truly prepared to endure over long periods of sustained torque. The John Deere D produced enormous low-speed rotational force. That slow, pounding torque was ideal for breaking hard soil and pulling heavy implements, but it also placed extreme stress on the drivetrain every single time the tractor started moving under load. Unlike smaller engines that built power gradually, this two-cylinder design delivered massive force in abrupt, uneven pulses. Each combustion cycle hit the clutch plates and transmission gears like a mechanical hammer. In daily farm work, this translated directly into accelerated clutch wear. Farmers would begin to notice slipping long before they expected any major service. The friction material degraded rapidly under repeated high-load starts, especially when pulling plows in compacted or wet soil. Once slipping began, heat built up inside the clutch housing, compounding the damage and accelerating failure. The transmission suffered its own form of silent punishment. Gears that were dimensioned for ordinary agricultural duty were suddenly exposed to stress levels more common in industrial machinery. Teeth wore unevenly. Shafts developed excessive play. Bearings that should have lasted for many seasons began failing prematurely. These were not isolated defects. This pattern appeared in farm after farm, across different regions and soil types. One of the most damaging aspects of this flaw was how it punished inexperienced operators. Farmers new to mechanical tractors often relied heavily on the clutch to regulate movement in difficult terrain. Every time the tractor was feathered into motion under load, friction skyrocketed. What felt like careful driving was, in reality, accelerating the destruction of the driveline. In heavy tillage operations, the problem became even more severe. The John Deere D was often tasked with pulling wide plows beyond what had been common only a few years earlier. As the plow dug in, resistance spiked. The engine responded with raw torque, but the clutch absorbed the full shock of that force before it ever reached the wheels. Over time, warped clutch plates became common. Springs lost tension. Engagement became inconsistent and unpredictable. Transmission failures carried even heavier financial consequences. Replacing worn gears, damaged shafts, or internal bearings required splitting the tractor. This was not a job that could be done casually in the field. It demanded time, skilled labor, and money that many small farmers simply did not have readily available. For some, a single transmission rebuild consumed an entire season's profit. Cold weather exposed another layer of vulnerability. Thickened lubricants increased internal resistance during startup. When operators engaged the clutch under these conditions, shock loads intensified even further. That sudden resistance traveled straight through the driveline, multiplying the stress on weakened components. Broken gear teeth and cracked housings became an all too familiar sight in winter maintenance shops. Many owners attempted field modifications to survive this flaw. Heavier clutch springs were installed to reduce slipping. Lubrication schedules were shortened in hopes of extending gear life. Some even limited the size of implements they pulled, sacrificing productivity to preserve mechanical integrity. These adaptations helped, but they also revealed the deeper truth. The original factory balance between power and drivetrain durability had been misjudged. What made this defect particularly bitter for many farmers was its contradiction. The tractor advertised strength. It was built to pull harder and longer than its predecessors. Yet the very system responsible for transferring that strength to the ground was one of its most fragile elements under real working conditions. Power existed in abundance, but endurance lagged behind. Over time, experienced operators developed a cautious style of driving the John Deere D. Smooth clutch engagement became a survival skill. Sharp starts were avoided. Loads were applied gradually whenever possible. This human adaptation became the only reliable defense against a structural mismatch between engine output and drivetrain resilience. This second hidden problem did not destroy the John Deere D's reputation overnight. Instead, it drained it slowly through repair bills, downtime, and mechanical anxiety. The tractor remained respected for its force, but increasingly feared for what that force could do to its own internal organs. The third hidden problem of the John Deere D lived in a place every farmer watched closely, especially in difficult economic years: the fuel system. Power alone did not guarantee success in the field. What truly determined survival for many farms was how long that power could be sustained before fuel costs swallowed profit. And here, again, the John Deere D revealed a deep and chronic weakness that shaped daily decisions and long-term operating costs. The engine of the John Deere D was designed at a time when fuel efficiency was secondary to raw pulling ability. Its two-cylinder layout, massive displacement, and low-speed operation produced extraordinary torque, but it also demanded an extraordinary appetite for fuel. Under heavy work, consumption climbed far beyond what many farmers expected based on published specifications. The carburetion system played a central role in this inefficiency. Mixture control was imprecise by modern standards. Fuel metering varied significantly depending on load, temperature, and altitude. In practice, this meant the engine frequently ran richer than necessary, especially during sustained high-load operations. Excess fuel did not translate into more usable power. Instead, it became wasted energy burned without benefit. Cold starts magnified the problem even further. To keep the large cylinders running smoothly during warm-up, operators had to enrich the mixture significantly. In winter, this process could last far longer than expected. During those minutes, fuel consumption soared while useful work remained near zero. For farmers working on tight margins, this daily ritual became a silent financial drain. Once warm, the tractor continued to consume disproportionately high amounts of fuel under moderate work. Tasks that other tractors could perform with restrained consumption demanded far more from the John Deere D's tank. Over long seasons, the difference became dramatic. The same acreage required noticeably more fuel than comparable machines from competing manufacturers. Fuel delivery stability also suffered under variable operating conditions. Changes in load could cause uneven mixture delivery. At times, the engine ran lean under sudden resistance, leading to brief power drops. At other times, it flooded under reduced load, wasting fuel and reducing combustion efficiency. Operators learned to compensate manually, constantly adjusting controls in an attempt to keep engine behavior predictable. This constant balancing act placed additional physical burden on the driver. Instead of focusing solely on the work in front of the tractor, attention was divided between soil conditions and mixture control. The tractor demanded continuous supervision not only mechanically, but economically. As fuel prices rose over the decades, this weakness became increasingly painful. A tractor that once seemed affordable to operate slowly transformed into a costly necessity. Some farmers reduced working hours just to control expenses. Others delayed upgrades they could not afford because fuel costs eroded their ability to save. Attempts to improve efficiency through field modifications became widespread. Jet sizes were altered. Different carburetor components were tried. Some owners experimented with aftermarket intake revisions. While minor gains were possible, none of these solutions fully corrected the fundamental design limitations. The engine architecture itself imposed an efficiency ceiling that could not be easily surpassed. The impact of excessive fuel consumption went far beyond operating cost. It altered how farms were managed. Work schedules were tightened. Certain tasks were postponed until absolutely necessary. Long-distance field operations were avoided whenever possible. The tractor's range under load imposed practical limits that reshaped daily routines. This third hidden problem exposed the economic side of mechanical design. A tractor could be powerful and still quietly undermine the stability of the operation it was meant to support. For the John Deere D, fuel inefficiency was not merely an inconvenience. It became a long-term burden that influenced every season of its working life. Over time, many farmers accepted this flaw as the price of strength. They learned to live with high consumption in exchange for pulling ability that few machines of its era could match. Yet the truth remained unchanged. The fuel system of the John Deere D was never optimized for efficiency under real-world agricultural demands. The fourth hidden problem of the John Deere D was not buried inside the engine or the transmission. It was felt directly in the hands, arms, and shoulders of every operator who spent long days behind the wheel. It was a flaw that did not destroy components overnight, but instead wore down both machine and man through fatigue, loss of precision, and constant physical strain. The steering and handling system of the John Deere D exposed a serious limitation when the tractor was pushed into real-world field operations. From the factory, the steering system was purely mechanical, heavy, and unforgiving. At low speeds, especially under load, turning the front wheels demanded enormous effort. When pulling heavy implements, weight transfer from the rear axle reduced the effective grip of the front axle. This made steering not only difficult, but at times unpredictable. The operator could turn the wheel with full force, yet the tractor would respond slowly, reluctantly, or unevenly. In straight-line work on flat ground, this weakness could be tolerated. But farming is rarely flat. In uneven fields, on sloped terrain, or when crossing soft soil, the steering behavior became a genuine operational risk. As one front wheel encountered more resistance than the other, the tractor could suddenly pull to one side. Correcting that movement required rapid physical force, often more than a tired operator could safely deliver. At low speeds during plowing, the problem became even more pronounced. Turning at the end of rows demanded repeated full-lock steering input. Over a full day of work, this placed extreme strain on arms and shoulders. Fatigue accumulated quickly, and as exhaustion increased, precision decreased. A tired operator meant delayed reactions, poor line control, and greater risk of accidents. The steering geometry itself contributed to the issue. With limited mechanical leverage and no hydraulic assist, every change in direction transferred directly into physical load on the steering wheel. There was no buffer, no system to absorb shock from uneven ground. Every bump, furrow, or embedded stone traveled straight through the front axle and into the operator's hands. Handling problems were further amplified when operating with heavy front-mounted equipment or under soft soil conditions. In mud, the front wheels struggled to maintain consistent directional control. Steering input could result in delayed or exaggerated reactions once traction was suddenly regained. This created a dangerous oscillation effect, especially at transport speeds along uneven farm roads. On slopes, the danger increased dramatically. The tractor's high rear weight bias combined with limited front-end authority could lead to sudden downhill drift when traction shifted. Correcting this drift required immense steering force at exactly the moment when the operator had the least physical leverage. Several historical accident reports from rural regions describe rollovers and implement collisions that traced directly back to loss of steering control under load. Another dimension of this problem appeared during transport between fields. While the John Deere D was never designed as a high-speed tractor, farmers frequently drove it on rural roads to reach distant plots. At those slightly increased speeds, steering sensitivity changed. The same heavy steering suddenly became less predictable. Small corrections could turn into exaggerated movements, forcing constant overcorrection and increasing the risk of road departure. Because of this, many farmers developed defensive driving habits. Wide turns became mandatory. Sharp cornering was avoided entirely. Loads were reduced not because the engine lacked power, but because the operator could not safely control the direction of the machine under full stress. Some owners attempted mechanical improvements. Front-end weights were added to improve steering authority. Linkages were rebuilt repeatedly to reduce play. Tires were changed in search of better grip. These adjustments improved behavior marginally, but never transformed the fundamental handling character of the tractor. The physical toll of this defect cannot be overstated. After years of operation, many farmers associated the John Deere D with chronic arm, shoulder, and back fatigue. The tractor demanded strength not only from its engine, but from the person trying to control it. Over long seasons, this fatigue reduced productivity as surely as any mechanical failure. This fourth hidden problem did not show itself in broken parts on a workbench. It appeared in the exhausted posture of operators at the end of the day, in the slow and careful way the tractor was guided through difficult terrain, and in the constant tension required just to keep it moving on a precise line. The John Deere D could pull relentlessly forward, but turning it, positioning it, and controlling it under real farming conditions was a daily physical battle. Power existed in abundance. Control did not. The fifth hidden problem of the John Deere D was the most silent, the most deceptive, and often the most destructive of all. It did not announce itself through slipping, overheating, or loss of control. It revealed itself through hairline fractures, through microscopic separations in metal that slowly grew under years of relentless mechanical stress. This was the problem of structural cracking in the frame and in the large cast iron components. The John Deere D was built to pull with brutal force. Its massive engine, heavy rear axle, and rigid construction gave the impression of absolute indestructibility. But deep inside that strength lived a vulnerability rooted in the metallurgy and in the way stress was distributed through the structure. Each time the tractor pulled a heavy plow, hauled a loaded trailer, or worked through compacted soil, enormous forces traveled through the chassis and into the cast components. Cast iron is strong under compression, but it is unforgiving under repeated flexing. The frame, transmission housing, axle supports, and engine mounting points were all subject to cyclical loads. These loads did not break the metal instantly. Instead, they created fatigue. Over thousands of work hours, tiny internal fissures formed. Invisible at first. Silent. Growing one stress cycle at a time. The most vulnerable zones were consistently the same. Rear axle housings. Transmission casings. Engine block mounting surfaces. Drawbar attachment points. These areas bore the highest torsional and tensile loads when the tractor was pulling at full effort. Each jolt from uneven ground, each sudden resistance from buried roots or stones, sent a shockwave directly into those cast structures. Farmers rarely discovered the problem early. Cracks often remained hidden beneath layers of oil, dirt, and grime. By the time a fracture became visible, it had usually been growing for years. Oil leaks appeared where there had been none. Gear alignment drifted subtly out of tolerance. Bearings began to fail for no obvious reason. What looked like random mechanical trouble was often the symptom of a deeper structural failure. Once a crack reached a critical length, failure could become sudden and catastrophic. A rear housing could split under load. A transmission casing could rupture during a heavy pull. When that happened, the tractor was instantly immobilized. Unlike clutch or cooling issues, this was not a problem that could be limped home. Structural failure meant total shutdown where it stood. Repairs were costly and uncertain. Welding cast iron in the field was never reliable. Even in a proper workshop, success was never guaranteed. The metal had already been weakened by fatigue. Preheating, slow cooling, and specialized welding rods were required just to attempt a repair. And even when successful, the repaired section rarely regained its original strength. Some farmers resorted to drastic reinforcement methods. Steel plates were bolted across cracked housings. External bracing was added to support failing sections. Drawbar mounts were rebuilt with improvised reinforcements. These solutions extended service life, but they also added weight and altered stress distribution, sometimes shifting the problem to a new location instead of eliminating it. The structural cracking issue also exposed the long-term cost of overworking beyond the design margin. As farm implements grew larger and heavier over time, many John Deere D tractors were pushed far beyond what their original structure had been dimensioned to endure. The engine could often handle the load. The frame quietly absorbed it, until it could no longer survive. This fifth hidden problem reshaped how experienced operators viewed the machine late in its working life. The tractor was no longer judged only by what it could pull today, but by what it might fail tomorrow. Every heavy job came with an invisible question: is this the task that finally breaks the frame? Unlike overheating or clutch wear, structural cracking did not offer gradual warning through performance decline. It offered uncertainty. A tractor could work reliably for years after the first crack formed, then fail without warning under a load that had been routine for decades. In this way, the John Deere D carried a hidden timer within its own structure. The stronger it worked, the closer it moved toward an unseen breaking point. Strength and fragility existed in parallel, bound together inside the same cast metal. This final problem reveals a harsh truth of early heavy tractor engineering. Brute strength often arrived before long-term structural endurance was fully understood. The John Deere D did not fail because it was weak. It failed because it was pushed into a world of forces its own structure was never truly meant to survive indefinitely.